Hello and welcome to this live demonstration of the Simplified Data Model concept, one of the key features of TADM's 7.3 release. The purpose of this presentation is to show how users of TADM can leverage the Simplified Data Model classes along with open IDs, redesigned extended attributes, and extended instances to quickly develop scripted custom sensors. These customizations can be used when creating new sensors or when editing existing ones. This demonstration includes a quick review of a simple scripted sensor for MongoDB, a presentation of the UI created for generic classes of the simplified model, how to create a simple grouping pattern for topology generation, and how to query objects with the new MQL operator eval. Before I get started with the demo, understand that the MongoDB server is already installed on this machine as a service. Okay, let's start with creating a proper custom server template using custom server. Here are templates of sensors that can be triggered by generic server sensor if it finds up and running processes that match the template's criteria, or it can be run as custom app server sensor along with a series of extensions, commands, or scripts. Here's an example template for MongoDB server. In opening its details, we can see that its name is MongoDB. It will store objects of app server. It is marked as discover, so it's not a definition of something we want to ignore. It's enabled. I picked an icon, something like storage, and below are the most important or most crucial parts, the identifying criteria. In this case, a sensor will be executed when generic server sensor finds a process that contains the name mongod.exe. Make sure that your template is below the last entry, which makes TADM ignore everything else. Here's an example of scope for MongoDB. It's localhost because our MongoDB runs on the same machine as TADM. At this point, we are ready to run a simple default discovery with our scope and level 3 discovery default template. However, in this case, we would discover only runtime process objects and see nothing more. So now let's try to configure an extension for our template sensor. We go into TADM's home directory and then into the dist etc templates commands subdirectory. Here we create a file that has the same name as our template defined in custom servers. The content of this file will be executed once custom app server sensor kicks in. Now let's see the contents of this file. Okay, here's the MongoDB file, and the content we see is a script line inside. This particular line tells TADM sensors to execute this script from this path located in the extension scripts subdirectory. It's a Python script, mongodb.py. It will be executed with the use of the newest Python Java engine, which can be seen here in the square brackets. It will be Jython engine version 2.5.3, which is a new feature of this release, so you can use the new syntax of the language. Alright, let's take a look at the contents of the script. This is the actual sensor we want TADM to execute. It's a core of this presentation. It's a small sensor, but we'll show you how we will address some of the big problems we had with previous data model. It will use simplified class objects along with open IDs, extended attributes in a much simpler way than before, and a new feature, extended instances. Finally, we'll see how our UI handles those objects. The old common data model contains over 1,500 types. It took a lot of time to extend it. It was impossible to create a generic UI for it, and it caused problems with performance of the persistence layer. It is very easy in this sensor to pick types to use because there are only 7 types now. Specifically, those seven types are S computer system, S software server, S function to represent some additional roles or functions of those two, S physical file to represent contents of a configuration file, S deployable component to represent something we introduce in this release as mid-level objects. In this example, a database will be such an object since it can be deployed on many servers. Also, S software installation to represent physical installations, execs, libraries, etc. And finally, S logical group to store information about clusters, collections, or any other kind of grouping the sensor discovers contain. All of these types are gathered in the com.collation.platform.model.topology.simple package. You should not use any classes other than those in your sensors. This specific sensor, was written in 2 to 3 tries. It took around 4 to 5 hours. 95% of that time was spent writing proper parsing for the command output. At this time, I'm not going to dive too deeply into the script. Most of its code is just the parsing. What I'd like to do is to focus on using the simplified model. Okay, so here's the default beginning of the sensor. Here we see parameters passed by platform named targets. We have an operating system object. We have a result where our objects will be attached. We have an app server that represents runtime processes that matched our template's condition. There's a seed object that triggered our sensor, a logger, and some environment settings. Further down, we find the major point, the creation of the main object. Software server class was picked, and here are 2 very important attributes, hierarchy attributes, which will position a CI represented by this object of a map of domains. Up until now, there were many specialized classes to represent proper types of CIs. For example, to represent Linux, a sensor had to store the Linux Unitary Computer System object. To represent Windows, the Windows Computer System object. To store the WebSphere Server object. To store JBoss, the JBoss Server object. Now, all of those classes are deprecated. Instead, we use generics and set proper hierarchy domain and type values. So with those 2 attributes, a sensor can specify what exactly is this computer system or software server or logical group. Both of these attributes are simple strings. Here we promote a convention approach over a configuration approach. Domain should be used in a similar way to package names. We separate different domain levels of domain names with dots. The most left one is the most general. The rightmost one is the most specific. For example, here we have app for application server, DB because it's a database server, and MongoDB because it's a particular database, MongoDB. And this object in the domain of MongoDB represents a database server, so we set the type to MongoDB server. Once you have your object, you have to name it, meaning you have to set some attributes and define a naming rule by telling Tatum which ones constitute a unique value. For servers, we usually use the primary service access point that's created from the machine's primary IP address and the port that the service listens on. In this script, the IP address and the port number passed by the seed object was used. TADM uses naming rule attributes to calculate globally unique identifiers, or GUIDs. Up until now, every attribute that was a naming rule attribute had to be hard-coded as such. Therefore, if you wanted to create a naming rule, a new release of TADM was necessary. Now we see our first step towards open naming rules. The first step towards a scenario where a sensor sets some attributes of an object, pushes this object for storing, and tells TADM those 2 or those 3 attributes are a naming rule for this object. If you calculate a GUID from them, it will be unique. We are not there yet, but it's a first step. A new attribute type called OpenID was created for this purpose. It's a wrapper for a string attribute that gathers all values you want to be the basis for calculation of a GUID. It makes sure that they are arranged in the same order every time. The underlying engine will create a full string value out of it and use it as the basis for the GUID calculation. All a sensor has to do is to add all of the naming values in the ID object. This type is designed as a string buffer, so a sensor can do chain adding, and then just set this object as a value of the attribute OpenID. And that's it. Our software server object representing discovered MongoDB server is ready for persistence. Beyond the OpenID attribute, some additional predefined attributes were set in this script. For example, instance ID is set to the same value as OpenID, but it's a nice display name notation. Also set was a host computer system used to attach the server to a computer system and passed by a platform as an operating system object attribute. So this is the moment when we set our result object with our server. Even if the rest of the sensor fails somehow during discovery, at least our sensor will bring back that much information. It's a good practice to create a sensor in such a gradual way, to discover as much as it's possible. Now let's briefly see the rest of the sensor. If successful, it will return some information about databases available on this server. There's a lot of code, and I'm not going to analyze it all. But here, for example, is a portion that parses arguments of discovered processes and extracts the home directory. Okay, and here we find a token that contains the mongod.exe string, and it extracts the home location. And here the sensor sets a logical attribute to false to point out that this is a physical server and not a virtual one. Here the dblist command uses the instance home to run the command mongo dump.exe. It further uses the hard-coded C temp directory to create files with the database's content. A well-designed sensor would extract the location of temporary files from environment or variables or via a command. But in this instance, it was hard-coded simply to simplify. All right, as before, we use the sensor helper module to run the commands, which is an imported module as shown here. Alright, at this point we run the command and receive the output, which looks like this. It contains the database string, this list of files, collections for each database, including the admin database. And back in the script, this output is split by new lines we use to pass to the function extract databases. The extract databases function does something interesting. It uses two different containers for data, and I'd like to show that now. The first one is a container for extended attributes. Until now, using extended attributes was quite painful. They were limited to 100 attributes per common data model type, which was not enough. Probably this was because there was no good place to store entire sets of data anywhere. So usually the sensor had to separate them into a collection of key value pairs and store them as extended attributes instead. The extended instances feature will solve this problem. You'll probably never again have to store more than 100 extended attributes, and I'll tell you more about that in a minute. Previously, extended attributes had to be stored separately from a CI with use of user data type objects via Data API. Querying them was a nightmare. First, you had to store your CI, then receive the GUID, and then call set extended attributes on Data API. Now it's all much more simple than this. Now a sensor can store extended attributes along with the CI using the XA attribute. Let's look at an example. The sensor creates an object for discovered database using the sDeployable component type. It sets its hierarchy with the same value as previously, which is app.db.mongodb. We're still in the same domain. But it sets its hierarchy type to database. It sets a simple OpenID for this database. That's assuming that no two databases on the same server can have the same name. So name is a good naming rule here. It sets a predefined attribute name and attaches this component to a server with the software server attribute. Then this database object is added to a list which will be required later. And now for this newly created database, two containers are created. Extended attributes data object for extended attributes kept in the XA attribute of our server, and extended instance data object for large chunks of data kept in the XD attribute of our server. For a sensor to be able to store an extended attribute, first you have to define it for a given data model type. So here is the place to do that. We look for sDeployable component here, and you can create an attribute. Another change we made in extended attributes is that we categorize them. The default category is general. All current extended attributes will be migrated to it. But now you can group your attributes in custom categories. So the has database index def attribute was defined for our class. It's Boolean in the category general. I also defined an attribute for software server type, found here. It's now a counter for discovered databases, database count, an integer in custom markers category. Now going back out to the script, this part of the script is not so plain because of the processing of the mongodump.exe output. But the crucial part is this. A sensor creates extended attributes data object, attaches it to a CI, and then adds attributes to it via add attribute, passing the name of the attribute if it adds it for a default category and its value. Once all attributes are gathered, it calls to XML, and that's it. Well, let's take a look at a simpler example. Below are extended attributes for a server object. As you can see, a sensor creates extended attributes object, adds all the attributes, here database count for category marquees, pulls to XML method and sets XA attributes of the server object with it. Now let's take a look at the other container that allows you to store larger amounts of data. It's the XD attribute of the server object of type extended instance data. Nothing has to be defined here, like in the case of extended attributes. That is, extended attributes are validated when a name is misspelled or type invalid. Those will not be stored with the CI, but extended instances are stored without any validation. This object allows you to store basically anything. It can be plain text, such as command output. It can be XML. It can be JSON format or CSV. Every instance has its type, and general is the default. In this sensor, we use XD to store the contents of the files that represent the inner structure of our databases. It does skip binary files. The script reads the file contents with the read content function defined at the beginning of the script up here. And store it with the add instance method using file type as the instance type and JSON enumeration value, which is useful for code and will be useful in the future because the generic UI will be able to detect the format and display it formally. And finally, the script passes 1 as true to indicate that we want this content to be visible on details panels. Notice that recognize that some internal XD instances are hidden and they pass it as 0 or false. Okay, so let's give it a try. As you can see on our UI, there's a new category called generics, where we'll see objects from Simple Package. So let's start a discovery on our scope. And we should see custom server agent for MongoDB stored with a green status. And here it is, green, so we have success. All right, let's go back to the console and check it out. All right, let's refresh the console, and here we have 3 deployable components representing 3 databases and 1 software server for our MongoDB server. Okay, let's click it and see. All right, there's our OpenID, IP and port, class name, which is generic. But here we have hierarchy domain and type concatenated to show what this CI actually represents. Let's see the details page. We have OpenID, logical flag set to false, and instance ID, instance home extracted from our command line parsing, hierarchy domain and type, object type, and we can see our deployable components here. Now, regarding extended attributes, there's nothing more in the General tab. However, we can see the Markers tab, and here we have the database count set to 3. Okay, let's go into Inventory Summary. We enter a generic software server folder, and we see a folder representing the app.db.mongodb domain. We enter and we see MongoDB server type, and we enter and we see our server. We click on that, and the details page shows. If you see a plus icon here, it means that this object can have deployable components attached to it. We don't know yet if it has it, but it can. So if you click this plus, you will see deployable components for this server. In this case, 3 databases. We can check the admin database, and we see that there's nothing really noteworthy here. But Module 1 and 2 should have extended attributes and instance sets. So here it is in the General tab. There are our default extended attributes. Notice there's no Extended Attributes tab anymore. We also have extended instances on a separate tab, representing type of this instance. If we click it, we can see the contents of this instance, which is some JSON representation of the database structure. Of course, we can find our objects on many reports here. Change history, for example. Run the report. And here we see how we show changes of particular extended attributes now as XA, and include the category.name in brackets. Okay, let's run a component comparison and compare 2 deployable components. Module 1 Okay, we are Module 1 and Module 2. And all is different, apparently. You can see the full content of extended attributes and extended instances. Now, let's create a topology for the objects we stored. We create a grouping pattern. We create a selector for it to find our core CI. Which is software server type with hierarchy domain. Set to app.db.mongodb. All right, I hit test, and yes, it works. So let's finish with the defaults. Yes, the grouping pattern is ready, and let's make Tatum execute it. Okay, we see it is in progress. Our agents are working, preparing the graph for us. give it a minute and then refresh our view. Yes, it's done. So let's look for our application. There are many more already created by other demos. So let's look here. And here it is. So show topology. A couple of seconds, and here it is. Our MongoDB server, 3 databases deployed on it, and a computer system which hosts our server. If you want to query objects via the API, everything works as it did. Now let's see a new feature of MQL, a new syntax operator called eval that can be used in conditions put against XA and XD attributes. It is special because the attributes are stored in XML columns on Tatum's database, and the eval operator transforms the MQL conditions into a proper XPath query. Let's take a look at good and bad queries to see Tatum's responses. First, let's find software server in the MongoDB domain. Okay, yes, there it is. It's pretty big output. So let's run a wrong query looking for software server, but with XD values that are stored in deployable components. As you can see, the output is empty, but no errors. If we break the syntax of our XPath query, we'll see a pretty large complaint from our database that it received SQL that has a syntax error. Now let's correct this query with the proper class. So it will not be software server, but deployable component. Correct the syntax. And here it is. Now let's query for software server by its XA element. Also, we'll need to change the XML sequence here. Refer back to the code here. Change this to XML/attribute. And now remove this asterisk because there are no more elements below attribute. And we have our server. Alright, so what you have seen is that a correct XPath query will work here. This shows a very flexible operator that will allow quite sophisticated filtering. Alright, and that's about it. The script itself now consumes only time to write proper parsers. No extension of the data model is necessary anymore. All the objects can be queried with the previous MQL syntax and with use of the eval operator. We recommend development of any sensor by just quick run, launching commands, and putting their outputs as they are. This will allow a fast development of a sensor that brings all data it can find, but without painful reformatting. Then, identify portions that are crucial for dependencies, or that need to be displayed separately, and store them as extended attributes. Keep everything else as extended instances just for the purposes of change tracking. It should significantly shorten the time and effort to create a sensor. All right, thank you very much for your attention.